I think that's a fair way to say it. It was not as bad as you thought it would be. So let's just break it into two sections here. On questions 1 through 5, are there any on 1 through 5 that you really want to talk about? Yeah, Matt. 5. You want to talk about 5? Absolutely. 5, fine. That's totally fine. My other class wanted to know about 5. Now, did anybody come up with a good way that they want to start 5? Anybody come up with a good method? And do you see what I'm doing with the graph paper here? This grid stuff right here? Please turn on the grid when you do your work. I really like seeing that grid. It helps make things a lot clearer, a lot more helpful for me.
How did you copy just the...
There is a program on your Surface. It's called the snipping tool. You can use the snipping tool and take out any screenshots you want. So I will use that all day long. So that's the problem he asked about. This one right here. Does anybody have an idea about how to start this one? Anybody have a good idea about how to start it? Yeah.
We can break it into 2.
Absolutely. So what's really interesting about these, about teaching you really powerful integration or differentiation methods or really powerful math is you feel as though you need to use it all the time. Don't forget basic things like you can pull things apart into smaller pieces. You might look at that and try to do some creative thing where you like find some weird substitution and it all folds in on itself and the answer is 7. That happens sometimes, not always. In this case, what can you do with this? Break it into how many fractions?
I break it into 2.
2, yeah.
So we have 4x over 1 plus x squared.
Yeah, exactly.
Minus 2 over 1 plus x.
Correct, exactly. Minus 0 to 2a. Now, what are we treating a as? What is a in this? Sorry, I wrote that too much there. What are we treating a as in this problem? What is a? A is a what?
Constant.
It's a constant. If this wasn't a constant, we'd have multiple variables and we'd be at the last trimester of this course. So in this case, a is a constant, and you now have 2 integrations. 2 integrations. We're going to do them differently. Which one do we want to do first? The one on the left or the one on the right? Umi, which one do you want to do first?
The one on the right.
Let's do the one on the right, because what do you see? When you look at the one on the right, what do you see, Umi?
The integral of tan.
Yeah, tan what?
Or tangent of.
Tan what?
Oh, arctan.
Exactly. You might remember this. What's the derivative of tan inverse? What's the derivative of tan inverse?
1 over.
1 over 1 plus x squared, right? So if you were to integrate both sides of that, what happens when you integrate a derivative? What do you end up with? You're back where you started, exactly. So this means that tan inverse of x is equal to the integral of 1 over. Is that super helpful right there? Who thinks that's helpful? Yeah, what do you see right here? What do you see on this? Do you really care about that 2 in the numerator? Do you care about that 2 in the numerator? Yeah, you can yeah, exactly. So this is just minus 2 times the integral from 0 to 2a of, 2 is gone, sorry. 1 over what? 1 plus dx, exactly. Now, do you have enough information right there in front of you to finish this? Yeah, you do, because what do you know? Can you now integrate this?
Yeah.
Yes, you can. You absolutely can integrate this. I'm gonna leave it here. We've done this. We've done the brute force. We've done 95% of this side. The integral of 1 over 1 plus x squared is tan inverse x. So what do you now have? You have negative 2 times tan inverse of x. But what are we evaluating that from and to? 0 to what? 2a. So can you finish this part on your own if I leave this to you? What do you plug in first? 2a, and then you subtract 0. Right. Over here, though, can we do the same thing? Can we do the same thing? Can we use the same type of integration? No, you really can't. You really can't do the same thing. Does anybody know what method you need to use on this one? It's a different method. Anybody know? Yeah. Substitution. Now, last year you probably called it W substitution. I like calling it U substitution. Does it really matter what kind of substitution we call it? No. It really just calls into question why mathematicians tend to pick letters that all look the same. Like X and Y are put together, P and Q, M and N, W and V, U and V. I like calling it U substitution, and it might break my own reality if I start using W, so I'm just going to ask you to bear with me and let me call it U substitution. Is that okay? Is that an okay compromise? This is how I like to write U substitution. I know people like to do it differently. I'm a little bit completionist when it comes to substitution. I like to write it all out. So in this case, what are we going to let U equal to? Anybody want to take a guess? We're going to let U equal something. Yeah? 1 plus x squared, right. I like doing the differential right now, so du is going to be 2x dx. So what does dx equal? What does dx equal? This is just algebra at this point. What does dx equal? Du over what? So this method is called u or w or whatever you want to call it, substitution. So what do we get to do now? What do we get to do now? What's that word? Begins with s. Yeah, let's substitute in. So what do we end up with? The integral from 0 to 2a of 4x over, oh, instead of 1 plus x squared, what are we writing? U, and instead of dx, what are we writing? Come on. Du over 2x. What's the magical thing we can do now? What's the magical thing that this whole exercise allows us to do? This goes away, and that goes away, and it makes us so happy because how many variables do we now have? 1. That's what we want. We're in single variable land still. So now we have 4 times the integral from 0 to 2a of what? 1 over u du. Does that make you happy to see something like that? No, it doesn't make you happy?
If you have it too.
Oh, I forgot the 2 right there, so my algebra just failed right there. You're absolutely correct. Is this okay now? Is that okay? Can you finish that? There was one part of the course outline I'd hope you notice. You now have access to my notebook, correct? You've opened it up in OneNote. Because you have live access to my notebook, what does that mean is appearing on your surface as class continues? These notes. You are not required to write down anything that I put on the board through the surface because you are automatically getting it already. You can write down anything you want to write down. Some people need to take notes. That's how they remember things. That's totally fine. This right here is about as basic as the notation gets in this class. It will get crazier and weird and strange. Am I teaching you to be a stenographer? Someone who just takes notes? No, I'm not teaching you to do that. There is no requirement to take detailed notes in this class because you have live access to it. Here's also something cool. Sometimes you might ask me to like scroll up. Do I need to scroll up for you guys to see what's up above? No. You can go into my notebook and just scroll up and see whatever you want. As long as we have a decent internet connection, you'll have live access to everything that's already been put on the board. Does that make sense? I will, it's been pretty stable. I will sometimes say things out loud that I don't write down. So are you going to write some things down that maybe I don't get down myself? Sure. This is what I want you to avoid, spending 50% of your energy doing this. And then I ask you a question. I can't reasonably expect you to answer any sort of deep question if all you're doing is sitting there writing down a triple integral rotated around some like planar axis, okay? Something we do later. Some of that was just totally made up too. So again, don't sit there obsessively writing notes unless you feel as though you absolutely have to. Yes?
1 plus x squared.
Yeah, so do you see what Matt's saying right here? I just fell into a really, really common trap here. This is a constant, but what type of constant is A? It's a what kind of value? We're integrating with respect to x, correct? So we changed what we're integrating with respect to. We changed it to u. So those constants from 0 to 2a, so we're going from 0, where do you have to plug 0 in and where do you have to plug a in? Into the what? In for x, into the u equals 1 plus x squared. So once we finish this, and I usually when I remember and rejoin the math thinking, don't put the limits in until the end, and instead of 0 and 2a, what do they become? 1 and what? 1 plus what? 4a squared.
Why would you wait until the end?
I like doing it at the end because I like breaking it down into really 2 processes. What's the new thing we're integrating, and what are the new limits of integration? You totally can do it all right here. I'm primarily interested in you remembering what I just totally forgot to do right there, which was change the limits of integration. So usually you'll see me leave it as an indefinite integral until the end, because sometimes people do this. Sometimes people keep the right. So as written, this was wrong, right? 0 to 2a. That was not correct. So sometimes people will have like messy, non-specific work, and they'll say 0 to 2a and have this mixed in, and then change it and get the right answer. But the work along the way is technically correct because this line would be false. Does that make sense, everybody? So when you do that U substitution, you can do it any way you want. Just try to be as accurate as you can through that entire storyline. Okay, so let's chat about, honestly, the hardest thing about 6, there's 2 things that are a little challenging. One, did you cover L'Hopital's rule in AB calculus? No, so what did you need to do? Look it up. Is it a relatively straightforward rule? Yeah, but you got to look at it, so it's a little challenging. The second problem is, yes, I know the text kind of got messed up right there. Sorry about that. What did it say if you decode it? It's the limit as x goes to a of the integral from a to x of e to the t squared all over what? X squared minus a squared, like that. When you are asked to compute a limit, what is the first thing you should always check? What's the first thing you always check when you're trying to compute a limit? Before you do that, what's the first thing you always check? What happens if I changed it to this? How would you do this one? You just plug in 7, right? So the first thing you always check, and you were answering it correctly by coming up with the problem you run into, you check to see if you can just plug it in. Again, I could give you a really challenging limit and give you lots of ways to work with limits, but sometimes, you know how you compute the limit? You just plug the number in. That's it. In this case, can we plug in a for x? No, because what happens in the denominator? 0. Do we like having zeros in the denominator? No, we're not very big fan of that, right? So we're stuck. Now, if you look at L'Hopital's rule says that the limit of this thing is equal to the limit of the derivative of each numerator and denominator. So you can take the derivative of the top, you can take the derivative of the bottom, and take the limit of that new thing. The new thing has the same limit. Generally speaking, most of the time, what happens when you take the derivative of something? Does it tend to get uglier or nicer? It's not mostly nicer. Are there times when the quotient rule blows things up and makes it worse? Yes, absolutely. In this case though, you can apply L'Hopital's rule, but there's something you have to check first. What's the limit of the denominator? What does this go to? It goes to 0, right? What's the limit of just the numerator? See, x goes, what's a to a? 0. So the top goes to 0 and the bottom also goes to 0. This is called an indeterminate form of 0 over 0. You can only use L'Hopital's rule when there's an indeterminate form of 0 over 0, or there's another indeterminate form. Anybody run into what it is? It's similar to 0 over 0. Anybody want to guess?
It's just 0.
No, it can't. No. It has to be 0 over 0 or infinity over. No, infinity. The 2 indeterminate forms, there are several, but the 2 that you need to concern yourself with right now, just for this question, is it infinity over infinity or 0 over 0? Which one is it? It's 0 over 0. It has to be 0 over 0. L'Hopital's rule only applies to 0 over 0 or infinity over infinity. So we can apply it. The notation that you generally see is this. This is equal to, it has an h over it, the limit as x goes to a. Can someone tell me what the derivative of the denominator is on this one? What is it? 2x. Because a is a what? Yay. What about the top? It tells you in the question what you need to do on the top. It tells you to use what? What? Fundamental theorem of calculus. When you take the derivative of an integral, where are you? Same place you started. Exactly. So what happens when you take the derivative of that integral on top? What are you left with? E to the what? X squared. If I have something, and I'm doing the hand waving motion, there are lots of caveats to this, but if I integrate something and then take the derivative, I'm back to where I started. The caveat is, what's the upper limit of integration on this one? What's the upper limit? X, right? Chain rule always applies when you're differentiating. So when you first did the derivative of x squared, what's the derivative of x squared? 2x. Well, there's actually an invisible 1 on the outside, right? Because what's the derivative in terms of x? 1, right? So over here, what would have happened if this was, say, x squared up there? Times 2x, actually. That you have to use the chain rule. But in this case, the chain rule just puts a 1 outside, and we don't really write that in, do we? So in this case, oh, here we are. So we said that these two limits are the same. Can we compute the limit now? What do you always check? Can you? Can you plug in a? Sure can. What is it? E to the all over 2a. There it is. Voila. There it is. Well, to find the distance between the center of the circle, you need to know the centers, right? For this one, can someone tell me what the center is? -1, 3. Very good. Absolutely. Do we know what the center of this one is yet? What do you do in order to find the center of that circle? Ah, I love this. You don't, I know. It's not as cool. You're like, oh, I'm glad you have the excitement. If you complete the square, what can you find? You can find the other center, and then once you have 2 points, are you guys pretty comfortable finding distances? Decent-ish? You're kind of, maybe, sort of? Yeah.
Our class never learned how to
Love it. Love it. I'm going to bring Stan back, and you can teach, too, just for fun, you know? Completing the square, I'm not going to go over it right now. If you need to look it up, you can. There are tons of videos on YouTube you can look up for how to complete the square. You're just adding something to make it a complete square. That's it. And when you do that, you get a nice center. You get a center. You could also use the first derivative. If the function goes from positive first derivative to negative first derivative, it has to be a maximum, right? If it goes from negative first derivative to positive, it has to be a minimum. So you can do first derivative or second derivative. It kind of depends on if you have a second derivative. Is the second derivative always easy to find? No. Remember what we said? When you take a derivative, sometimes it gets nicer, but sometimes what happens? Boom! It gets terrible. Question, Umi? Okay, so here we go. A sequence. How many of you have studied sequences a little bit before? Yeah. It's an infinite list of numbers. Why do they have this subscript right here? What's with the subscript? 1, 2, 3, dot, 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 and dot, dot, dot. Why do we have a subscript? What do these numbers tell us?
It tells you where to.
Exactly, it tells us the order. The order is going to be really important in these things. We need to have them in a specific order. So when we deal with sequences, it's just a list. That's all it is. We need to define them. So here's one way we define them. We come up with a formula, essentially, for each of the terms. So on this one, if I want the first term, what do I plug in where for this one? For n. So it's 1 times 1 plus 1 all over 2, which is going to be 2 over 2, which is 1. If I wanted to get the next term, S2, I'd plug in 2. If I want the third term, I'd plug in 3. If I want the 10th term, what do I plug in? Did I do math wrong? No? Did I do it okay?
Can I ask you, is
Yeah?
this on somewhere notes?
15, right? 15 plus -1 to the 15 over 15. So what's that going to be? 15 what? I think it's minus all over 15. That's kind of cool. 14 over 15. Nice. So you can use a formula to get each term in the sequence. But there's another way we could go. Instead of going from the formula to the sequence, we could go from the sequence to the what? To the formula itself. So in this case, see if you can figure out the formula for each of these. There's 2 of them. For A and B, give a general term for the sequence, meaning find me Sn. Find me Sn. And we'll say n is starting, n is greater than or equal to 1 for each of these, okay? What the formula is going to be? Yeah, Matt. 2 to the n. Yeah. If it started at 1, you'd just be 2 to the n minus 1. It doubles every time. Yay. What about this one right here? What's the first thing you notice? What's one nice thing about it? There's a lot of 7s, right? Are there all 7s? So maybe what should you do? Change it to. Yeah, so change this into 7 over what? 14. So what do you want n to start with on this? Do you want to start at 1 or 0? What do you want n to start with on this one? Start with 0? Sure. I'll decide for you. So what's the numerator always going to be? 7. It looks like it's going to be 7. So maybe do Sn is equal to 7 over. What does it look like we start with down here? What should go down here? Anybody want to guess? 2 plus what? 2 plus 3n. Good job. Because what's the gap between each of these? 3. It becomes more apparent once you turn that into 14.
So what was the first one? Was the sequence
2 to the n.
equals to the n?
Mhm.
For the third term is 4.
Yeah, we're starting at 0.
Oh, okay.
I was making it easier for you by starting
Okay.
it at 0. If it started at 1, you can just shift it over 1 by doing n minus 1. That's it. Now here's the thing about creating these explicit formulas, sometimes they just pop out and you're like, oh, it's 2 to the n, and sometimes you work it a little bit. Can they be really hard to find out? Yeah, sometimes they can be crazy hard. Like crazy hard. We have time, right? We still have time. Yeah. These are visual representation of sequences. These are visual representations of sequences. So what's going on here? These sequences are going back and forth. This one is. So what does it look like this sequence is doing? It looks like it's converging. It looks like it's converging to a value, maybe 1, not that. Same sequence, but it's labeled because it's in 1 dimension now. Or 2 dimensions. 2 dimensions. Here's the first term, here's the second term, here's the third, here's the fourth, here's the fifth, here's the sixth. What does it look like the sequence is doing? It looks like it's converging. Weird. It looks like, so here's the first one, here's the second one, here's the third one, here's the fourth one, here's the fifth one, here's the sixth. It looks like the seventh, eighth. It looks like it's converging.
That's 2 dimensions, isn't that 1 dimension?
Yes, it is 1 dimension. I'm sorry. So I had a long day or something like that. I know it's 1 dimension going side to side. It looks like it's converging to 1. We're going to spend a lot of time looking at convergence. You already kind of know why, but why do we look at convergence? What does it help us do? Maybe again, not differentiate, it helps us integrate. When you first learned how to integrate, what was your first method for integrating? What was the first method? Do you remember pictures that look like this? They're insane. I'll draw it up here. You remember, you're like, oh, okay, so we have this parabola like this, and I'm going to draw all these things. Do you remember this? Riemann sums. You love that, right? And then no, I don't like that, right? And then you learned how to integrate, right? Using some shortcuts. But you had to. Did you ever have to write expressions for adding up an infinite number of rectangles? Right? Oh, you're adding a bunch of things together, and it's an estimation. But as you go to infinity, what does it approach? The actual area under the curve. Right? So we learn sequence of the curves, and then we add it together in series, so that we can create Riemann sums and do integration. Yes. It's fine. Oh, what would this be? Would this be left or right? Right hand. You look at where it touches the function. So look at one of the rectangles here. It touches at the right. This would be right hand. So this is increasing? What if it, well, you could draw it. What do you mean, what if? You can figure it out. You got it. So this would be right hand. No, I remember. Believe me, I experience every summer the same kinds of things that you do. So here's what I'd like you to do. I'd like you to give the first 6 terms of the recursively defined sequence, the most important word here being recursive. What does that mean? What does recursive mean? Take a look at the definition and tell me what you think recursive means. We've been doing explicit. These are explicit formulas right here. They're explicit because it's just in terms of n. To get the 10th term, you need to just plug in 10. What's this add in though? What's the difference now when you deal with recursive? Look at the formula. What do you see? You need previous terms. So do this for me. Write the first 6 terms of both of those. See, anybody have the first one? What do you have for A here? Anybody have it? It's going to go 4, then what? Yeah. 10. Yeah, it's a line, right? We have a linear recursion. Nice. What about the next one? What's this going to be? Negative 6, and then what? Not negative 18. I wrote that improperly. 18, and then to get bigger, yeah, what's it? Negative 54, and then what? And then what? 46. Yeah, it gets a little bigger. So you can recursively define things. Okay. So there are 2 types of definitions so far, recursive and explicit. There's a really famous what's probably, you know this, you might not think you know, but what's the most famous recursively defined series? Yeah? Sequence. Differential sequence, yes. 1, 1, 2, 3, 5, 8, 13, and so forth. What is the definition? What's the recursive definition for this if you had to define it? Sn. Let's do it Sn. What's Sn equal to? Yeah?
That's 7 minus 1.
Yep.
Plus that's 7.
Yeah, to get 1 term, you need the prior 2. So if you want the 10th term, you need the 9th and the 8th. But to get to 8th term, what do you need? 6th, 7th, and the 6th. If you need the 6th term, you need the 5th and the 4th. So is this a very efficient way of generating the Fibonacci sequence? Not particularly, because what happens if I wanted the millionth term? How many terms do you have to find first? 999,999, right? That's pretty slow. This is a recursive definition. What question might I ask you? What's the explicit? So here's the correlation, right? Let's start it at 1. 1 has to go to 1, 2 would go to 1, 3 would go to 2, 4 would go to 3, 5 would go to 5, 6 would go to 8, 7 would go to 13. So you were trying to come up with, don't start working on this. Don't.
Does it exist?
Yes. Here's the cool kind of biggest truth I can give you. Any recursively defined function has an explicit definition.
Mind blown.
You get to do things like that in a class in college in the field called combinatorics. You use these things called characteristic polynomials. This is particularly cool because when you see the formula for this, what do you expect to see? If I wrote the formula for this on it, you can Google it, explicit formula. Don't look it up right now. You can. Don't do it right now. I know you want to, which is good. What would you expect it to be like? Do you have any expectations for the formula? Some ridiculously crazy thing. It's pretty crazy, but when you look at it, it's not this big. It's like this big. It's like a couple things. It's pretty complicated, but not totally weird. There's no like inverse trig in it, but it has like root 5s in it. The golden ratio appears in it. It's really cool. So this function, when you graph it, at 1 it hits 1, and then it hits 1 again, and then it hits 2, and then it hits 4. It passes through all these points perfectly. It's really cool. But the biggest thing I can tell you is that anything that you can recursively define, you also can explicitly define. Yes?
If you graph it on
Do the same thing on these. Give me the recursive definition for these two. Give me a recursive one you get. Sn is equal to Sn minus 1 times what? 2 plus 1. You double the prior term, the previous term, and you add 1. You double it and you add 1. Cool? Huh? What about this one? What about that one? First of all, what do you notice about those numbers? What are they? They're all squares. Like this is 1 squared, 2 squared, 3 squared, 4 squared, 5 squared, 6 squared, right? So what's the explicit? What's the explicit one? It's just what? Let's see if n is greater than or equal to 1. What's the explicit going to be? It's just n squared. So in this case, is the explicit one really easy to get? Yeah, sure it is. So in each case, though, it wants the recursive for both. Does anybody have a cheap way of writing a recursive definition for this one? Anybody want to guess? There's a cheap way.
Sn minus 1 plus 1 squared.
Yes, yeah. So you could say like Sn is equal to Sn minus 1 plus 1 quantity what? Yeah.
wait,
Does that work though?
isn't it root of that?
Hold on. Yeah. Yes, it is. You answered the question and came up with a solution. Very good. Yes, the problem here is Sn represents the actual entry. What would you need to do? You would need to take the square root of the previous one, then add 1. So the cheap way of doing this would be to write it like this. Bingo. Not cool. Right? If you want the 10th term, you take the 9th term, square root it, add 1 and then square it. Because the next term is just the next on the chain of 1, 2, 3, 4, 5, 6, 7, 8. The next variable. It's pretty cool. I call that